Hello, so you're welcome to this lesson on integration. In our last lesson, the last video, we covered Riemann sums, and we did some examples, and I asked that you take a look at the examples and try them yourselves. There were a couple more that I didn't do that you could look at. In this lesson, we'll start off with the last bit that we didn't cover. We'll look at the distance problem and move on to the definite integrals and the rest of it, okay? Okay, so what is the distance problem? The question is, how do you find the distance that is traveled by an object, okay, during a specific time interval, if you know the velocity at all times, okay? So from point A to B, an object is traveling, and we know the velocity of the object. So can we tell the distance that is traveled within this time interval? That is the point. Now, if the velocity is constant, then it's straightforward. The distance is given by velocity times time. Or, the well-known formula is that velocity is distance over time. So if you multiply by time, you get this formula. So here's a simple example. If a car traveled along a straight line with a velocity of 60 kilometers per hour over a 2-hour period, okay? See a graph, a diagram in the next slide. If the velocity is this, time is between 0 and 2 hours, then the distance will be equal to the velocity, which is 60 kilometers per hour, multiplied by the 2-hour duration. Okay, so if you multiply by that, you have 120 kilometers. Now, the good thing about putting the units is that you can easily see that when you multiply the two quantities, hour cancels hour, and the unit that is left is kilometers, which is a unit for measuring distance. Okay. So that is the neat thing about using this. So if the velocity is constant, then it's easy. Then it's basically this rectangle. If you plot velocity as against time, the velocity is constant at 60 kilometers per hour. The distance moved on the x or the t axis is 2 hours. Okay, so you just multiply height 60 multiplied by the width, which is 2, that gives you 120 kilometers. So that's easy. Now, the interesting one is what happens if the velocity is not constant, all right? The velocity is a function of time. It's changing, okay? With time, it's changing. So knowing this, that the velocity is changing with time, can you still compute the distance that is covered by the object? That is the main question about the distance problem, okay? And the answer is yes, of course. We can just use what we learned under the Riemann sums to do that. If the velocity is not constant, but it's a function of time, the distance is just equal to the limit as n goes to infinity of this summation, all right? I'm sure you recognize this now, right? This is basically the Riemann sum. In other words, we are taking each rectangle. We know this is the velocity. If we take sample intervals and take a rectangle, right? If the distance between this is delta t, if you like, and the height is given by f of ti star, for instance, then if I multiply this by the height, I get the area under this rectangle. That area will be the distance traveled within that short period. And I can add all of them up to give me an estimate of the distance covered, or if you like, the area under the graph, right? And as we learned before, if you take the limit as n goes to infinity, then I get exactly the area under the graph, and that area will give me the distance that is covered. So the distance is the limit as n goes to infinity of this sum here. All right. So where, of course, delta t is the intervals, b minus a over n. Ti is given by this. And of course, ti star, you can use the right endpoints or the left endpoints, and you can compute it to get it. Okay, so it's not different from Riemann sums. If you want to find the distance covered, if the velocity is a function of time, all you do is find the Riemann sum of it. That's it. And the results will give you the distance covered. Okay, so I haven't really done an example on this because we have done examples on Riemann sums. Okay, so we'll move on to something else. We're going to move on to the definition of the definite integral. Okay, so the neat thing about the Riemann sums that we did is that it helps us to define mathematically what we mean by an integral. a definite integral from some point to some point. So here's a definition. If f is continuous, a continuous function in this interval, we have to divide the interval AB into n sub-intervals equal to this. We have seen this before. And then we can let this be the endpoints of the sub-intervals. And then what we do is that we choose sample points, which are given by this in these sub-intervals. As we learned before, the sample points could be the left endpoint, the right, or the midpoint, or any point in between, where this lies in the ith sub-interval. Then, here is the definition. Then the definite integral of f from a to b is given as this. Integral from a to b of f of x dx is equal to the limit as n goes to infinity of this summation. So this tells us that the integral that we know, that we have seen several times before, is actually defined as a Riemann sum, the limit as n goes to infinity of the Riemann sum of rectangles. So that is why the concept of Riemann sums is important. It goes directly to the definition of what we mean by a definite integral. Okay, so if you're asked to define a definite integral, it is actually this, the limit as n goes to infinity of that. Okay. You can read it over again and then try to understand this. Okay, here are a couple of remarks on the definite integral. Okay, since a and b, the limits, the lower and the upper limits are numbers, this integral is of course a number, it's not a variable. Secondly, this function f under the integral sign is not necessarily a positive function. If it's a positive function, you can always interpret it as the area under a graph, but it's not always positive, right? It could be negative as well. Okay, in that case, if there is positive and negative, you can interpret it as the difference between areas, between the positive and the negative part of it. So if f has both positive and negative values, then a definite integral can be interpreted as a difference of areas above the x-axis and below the x-axis as shown here, right? A1 is positive, A2 is negative. The difference will give you is actually this integral. So the integral could be negative or it could be positive. All right, so take note of that as well. Okay, so let's do some examples to illustrate that. So one thing we learned from that definition, okay, the definition of the definite integral, this guy. This definition is that you can go from the right-hand side to the left, or you can go from the left-hand side to the right-hand side. In other words, if I give you a function that looks like this, I can tell you from here, compute the Riemann sum, and you have to, from here, be able to do this. Or if I give you a Riemann sum like that, you should be able to convert this to the definite integral. Okay, so you should take note of that. The delta x here is the dx. The xi star is actually the x in your function here. It helps you to be able to go between the two. Okay, so this says express the limit as n goes to infinity of this summation, all right, as an integral on the interval 0 to pi. So we are given the interval. So a is 0 and our b is pi. 2 says use Riemann summation to compute the integral from 0 to 5 for x dx. So you are not going to do it as you do it usually. You are given this, but from here you have to get the necessary information you need to be able to compute the Riemann sum. In other words, find the limit as n goes to infinity of the summation thing. That's what you want to do here, this and that. Okay. All right. So let's do the first one. If you compare this to the definition of the integral, the definite integral from a to b of f of x dx, then of course we can write our f of x as what is in here. So our f of x will be x cubed, right, plus dx sine x. We know the interval is from 0 to pi, so our a is 0 and the b is pi. So we can plug these guys into the definition of the definite integral, so that from here we have equal to the integral from a to b, so 0 to pi. Our function f now is x cubed plus x sine x dx. Okay, so this one is straightforward. The function can be gotten from here. the A and B can be gotten from the interval that is given. Okay, and this is the second example. Question 2A says that we should use Riemann summation to compute this. So here we know that our interval actually, yes, so we have to subdivide our interval 0 to 5 into n sub-intervals by definition, right? And the width of each sub-interval is a minus b over n. B minus a over n. B is 5, a is 0, so over n, 5 over n. You have that. So you have delta x, we know that. Xi, I'm just using the right endpoints. Okay, in this case, it doesn't matter because we're going to take the limits. In all the examples, I'll be using the right endpoints because the formula is simpler. So for the right endpoints, xi is a plus I delta x. A is 0 plus I delta x, we just found to be 5 over n, which is this. So I get 5 over ni. All right, good. So now I can convert the definite integral to be equal to the limit as n goes to infinity of the sum of f of xi, okay, times delta x. Great. Now, this f of xi, if you compare to this, is actually 4x, right? Delta x we know, which is given by this. All right, so we have limit as n goes to infinity. Our function is 4x. In place of x, I'll put xi, right? So I have 4xi multiplied by the x, delta x, which is 5 over n. But xi is given by this, so I plug xi here. All right, if I put 5, yes, xi, 5 over ni over here, right? The 5, well, in the first place, I'm going to have 5 times 5 here, that's 20. That's all over n, which is this. And then xi, of course, is 5 over ni. Okay, so so you just put these guys into the formula. That gives you this. And we can just expand this. I can bring the 5 out. That gives me 100 over, and the n as well, 100 over n squared, and then sum the I. And then you have to go back, use the formulas for the summation. Sum of 1 to n of I is just n into n plus 1 over 2, okay? Here you can pull out your n, you have n squares cancel out, okay? 2 cancels this, you have 50 into 1 plus 1 over n, take the limit as n goes to infinity, this goes to 0, and you end up with 50, okay? So you can move from the definite integral and use the definition of the Riemann sum, right? To actually calculate the integral using Riemann sums, and that gives you this. You can check by doing this directly. This is very easy. So you can check. It should give you the same answer. Okay, the second problem, the B part, says that we should use Riemann sums to compute this. Okay, so we're going to do the same thing. Here, our interval is from 0 to 4, a is 0, b is 4, so I have delta x to be 4 over n. Okay, I'm using the right endpoints again. A is 0, delta x is 4 over n, so I have 4i over n. My function now, f of x, is given by this, 2x squared plus 3, which is this. So from here, I define it as the limit as n goes to infinity of sum of f of xi times delta x. So here, in the f, wherever I see x, I plug in xi. Xi is 4i over n, so I'm going to plug them in here and add 3. So I have 2 times 4i over n all squared plus 3, and I multiply by delta x. Delta x is 4 over n, okay? Then you just expand this. I can pull this out, okay? The square of this will be 16, of course, multiplied by 2. That gives you 32 over n squared, I squared plus 3. You have this. Multiply 32 by 4, you have 128 all over n cubed. That is n squared times n, that's n cubed. Apply the formula for summation of I squared, that is this guy, plus 12. That is, I'm going to multiply this by, know that if you sum 3, which is just a constant, you're going to get 3n, okay? So that n cancels this n, and then 4 times 3 gives you 12, all right? And then again, as we have done several times, you can pull n out and out, you have n cubed, which cancels this. And so this guy gives you this. This is just a 12. And finally, you should get 164 over 3 if you simplify this. So the rest of, from here, actually, from here, I can leave the rest out because this is just algebraic and you have done it in our previous lesson. So you get that, okay? The point is that you can move from this definite integral to using Riemann sums to find the value, okay? This is another example. We want to use Riemann sums to evaluate the integral from 1 to 2 x plus 1 dx. Actually, I will skip this. That is too straightforward and easy. While it's here, let's just do it. Our A is 1, B is 2, so delta x is 1 over n. I'm using the right endpoints again. Here, A is no longer 0, or maybe that's why I brought it. A is no longer 0, is 1, so I have 1 plus I, delta x is 1 over n, so I have I over n, okay? So our f of x from the integral is x plus 1, so f of x is this, which implies that this integral can be defined as the limit as n goes to infinity of the sum of, now I'm going to have f of what? F of x, right? F of xi, okay? So what I do is that in place of the x, I put xi, which is this guy, plus the 1, and that is why I have 1 here, okay? This will give you 2 plus I over n. If you compute this, so try it. If you compute this, you should get 2.5. Okay, good. So this is another simple example that you can try on your own. Now I'm going to give you a couple of exercises in the next page. But before you do them, actually I have the solutions in my lecture notes. I don't want you to look up the solutions. I want you to try them after you've seen this lecture. Try them. After you've tried them, then you can check the lecture notes and see my solutions. Okay. So before you do them, keep this in mind. These are equivalent. They are all the same things. This is the definition of the definite integral, which we just showed. This is an expansion of this. I'm just saying that xi bar can be written using the right endpoint, which is this, okay? And of course, this is also the same as this because delta x is just defined as b minus a over n. Delta x is b minus a over n. That's all. So these three are equivalent. So just keep that in mind. So these are the exercises. So look at them, take a look at them, go through them and try them out. This should be much more straightforward because we've just done something similar. Okay, so try these ones out. These are, you are not presenting them just for your own good. Okay, so the next thing we are going to look at is evaluating definite integrals. Okay, some of these you've seen before, but we want to prove the theorem. We'll prove the theorem for the so-called evaluation theorem. If f is continuous on the integral, on the interval, this is not integral, this is supposed to be interval. On the interval AB, then the integral this is equal to f of b minus fa, where f is an antiderivative of f, that is f prime is equal to small f, right? Capital F prime is small f. We've seen this before, right? The second part of FTC, the Fundamental Theorem of Calculus, right? That is where we saw this. And I asked that you prove it. So I'm going to show the proof here now, okay? You know how to apply it. We'll do a couple of examples. So let's prove the FTC part 2, the evaluation theorem. So how do you prove that? How do you prove this? That f of b minus f of a is the same as the integral of a to b f of x dx. That's the point. Okay, so what you do is that we are going to use an idea similar to Riemann sums. You divide the interval into n sub-intervals with endpoints x0 to xn, and with width delta x is b minus a over n, where a is x0 and b xn. Okay, now we know that f of b minus f of a is equal to f xn minus f x0. All right, because x0 is a, right? Xn is b. So this is not strange. It's the same thing. Okay, good. Now here's the tricky part of the proof. We say that this is equal to, now I can subtract and add. This is the same as this, so they cancel out. So I haven't really done anything. This and this are the same, so they also cancel out. I can do that all the way to the last point until I subtract minus f of x1 plus f of x1. They cancel out as well. And finally, I have minus f of x naught, which is the same as this. So basically, this next line is the same as this because I've just added zeros in between. Okay, I haven't done anything. I've just added zeros. Good. But now that I have done this, I can group the terms, all right, in twos. I can group these first two terms. I get this. I can group this guy and this. I have that all the way to the last two terms, which is this. Okay, I can use the summation symbol to rewrite this in a nice form, that f of b minus f of a is equal to the sum from I cos 1 to n of, all right, f of xi minus f of xi minus 1. Okay, just look at these guys. When I is 1, you get this first. When I is n, you get these guys. Okay, so this is the same as that. Good, good. So we have this. So from here, we know that the function f is continuous. This antiderivative of f, all right, is continuous and differentiable because capital F prime is small f. So it's continuous and differentiable on this interval. Because of that, we can actually apply MVT, the mean value theorem, to it. MVT says that if this is continuous and differentiable on an interval, then there is a point within that interval, right? Xi star, we are calling it. And when you learn MVT, we're using C, right? Or some number. So there is an Xi star within this interval such that F prime at X star is equal to F at Xi minus F at Xi minus 1 all over the difference between them, right? If you apply the formula of MVT, you get this. You can multiply through by the denominator here, and then you're going to have this numerator is equal to this guy multiplied by the denominator, which is this. Okay? But remember that capital F is the antiderivative of small f. So big F prime is small f, okay? And the difference between xi and xi minus 1 is delta x. So this is equal to that, okay? So this is equal to this. And so if you go back to the previous equation, right? This equation, what we've determined now is this. So we can put it back here, all right? So if you go back, if you go to this, so we substitute equation 5 into equation 4, and we're going to get this is equal to the sum of f of xi star delta x. Okay? Now you can take the limit as n goes to infinity. The left-hand side has no n, so it remains as such. And the right-hand side gives you limit as n goes to infinity of this summation. But we recognize this, right? This limit is the definition of the definite integral. So this is actually equal to the integral from a to b of f of x dx. All right? So we have proved that the integral from a to b of f of x dx is equal to capital F of b minus capital F of a. This is what we wanted to prove, remember? So we have proved the FTC2, the second part of the Fundamental Theorem of Calculus. In this case, we call it the Evaluation Theorem. All right? Good. So this is a simple example that we can do. Find the area under the cosine curve from 0 to b, where b lies between 0 and pi over 2. Okay, I've drawn the cosine curve here. You can, this is easy. From 0 to p, we integrate cosine, we get the integral of cos is sine from 0 to b is equal to this. Sine of 0 is 0, so I have sine b. Of course, when b is pi over 2 at the end point there, then sine of pi over 2 is 1. So the area under the graph, right, from 0 to pi over 2, the area under the cosine, if you integrate it, you get 1. Because it's 1, that's why it's interesting, nothing more. It's not a difficult problem. Okay, good. So we just apply the evaluation theorem to this. These are a couple of properties that you've seen before. I'm not going to dwell too much on them. You've seen most of this. Most of this I actually hold on. This is telling me that my screen sharing is paused. Okay, I'll try and fix this. Hopefully, I'm still sharing my screen. Let me see. Don't pause it. Okay. Okay, so I'll just stop sharing and continue sharing again. All right. Okay. Okay, so we are back on. Okay, good. So I was saying that I'm going to do a couple of, I just wrote down a couple of properties. You don't need to memorize this. I mean, you've seen most of this before. If I'm integrating from a to b of c dx, of course, I just pulled out the c and then I integrate this, I get that. If I'm integrating a to b of the sum of two functions, I can split it into two, right? I can do this separately and that separately. This is similar to this. I can pull c out and integrate the function f. C is a constant. This is very similar to this. It's the same. I don't know why I put it here. If we are integrating from a to b of f of x, you can split your interval into a to c, where c is some constant, f of x plus c to b of f of x dx. All right. We have seen this before, right? There are comparison properties of integrals. If this is positive, the integral of it is also positive. Okay. The same thing here. If this is greater than this, the integral of this is greater. If f lies between m and m, if it's bounded, of course, the integral is given by this. We showed this in our first lecture. Okay. Now, if you're integrating a to b of f of x, this is the same as negative b to a. If you interchange, if you switch these guys, then you have to put a negative sign here. All right. And if you're integrating from a to a, the same number, or x to x, or t to t, your answer is 0, basically a point. So it's 0. Okay, good. So these are some examples to illustrate it. Use the property of different integrals to evaluate. You can do this. I'll skip them. This is easy. Number 2. Okay, we're going to do 2. 2 says, given that the integral from negative 2 to 2 of f of x is 3, and the integral from 0 to 2 of f of x dx is 2. Evaluate these. Okay, this guy, and that. So I will do these ones. These are more interesting. So you can try the first one. So 2 says that we are given this and this, and we want to find the integral from 2 to 0 of f of x dx. Of course, 2 to 0 is the same as the negative of the integral from 0 to 2 of f of x, but we know the integral from 0 to 2 f of x is 2, so we just have negative 2. So that's straightforward. This one says that we need to compute integral negative 2 to 0 of f of x plus 3 dx. Of course, we are just going to use the properties. We split this into two integrals, this guy and that guy. Okay. Now, we know this. Okay, negative 2 to 2 is given by this, so we're going to use it. Now, negative 2 to 2 f of x is equal to, I'm going to split this from negative 2 to 0 plus 0 to 2. Of course, this guy is 3, so 3 is equal to negative 2 to 0, plus this guy, 0 to 2, is given by 2, so I have 2 here. I can bring the 2 to this side. 3 minus 2 is 1, which means that integral from negative 2 to 0 is 1. Okay? So I can go back to this, and I'll say negative 2 to 0 of f of x plus 3 is equal to, note that I split it in 2. This one gave me a 1, all right? And this, I can pull out a 3 and integrate negative 2 to 0 of dx, okay? This is just x from negative 2 to 0. That's easy to evaluate, and your answer will be 7. Okay, so that is straightforward. And then let's go to the last one. The last one, we want to compute this difference. Integrals 2 to 0 of 3 f of x minus the integral from 0 to minus 2 f of x dx. Again, this is just applying the properties that I just outlined there. This, I can pull out a 3 I can pull out a 2 and I have this. This guy we already know, right? We know that integral from 0 to 2 of f of x is 2. So 2 to 0 is -2, which we found already. The integral from -2 to 0 is 1. So the integral from 0 to -2 is -1. So I have the -1 here. So simplify this and you get -4. Okay? So that gives us the solutions to what we're trying to do. Great. Now, so that is basically on the definite integral. The next couple of things that we'll be doing will be on the indefinite integral. Sorry, on the indefinite integral. I just have about 4 slides, so I'll just try to cover them and then we'll bring this lecture to an end. Okay. Once you know Riemann sums, you know the definite integrals. Indefinite integrals should be straightforward. All you need to know is how to find the antiderivative of the integrands. That's it. So in the indefinite integral, of course, you don't have a to b because you don't have any numbers on the limits. If f of x is an antiderivative of small f, that is, if f prime, capital F prime is small f, then the integral of this is, of course, equal to the capital F of x. Remember that if we had a and b, then this is given by f of b minus f of a, right? Then the indefinite integral, this guy is a function, okay? While the definite integral, this is a number. So that's one of the differences. If you do a definite integral, you get a function. So we can just use that idea to evaluate this, okay? Again, these are straightforward because you've seen most of these already in our previous classes. Okay, so integrate x to the n, you add 1 to this and divide by it. You have x to the n plus 1 divided by n plus 1 plus your constant of integration. If you integrate e to the x, you get the same thing plus your constant of integration. The integral of sine is negative cosine. Integral of 1 over x is ln of absolute value of x plus c. Okay, good. Verify by differentiation that the following formula is correct. So you want to verify. In other words, we know this is the antiderivative, right, of this function here. So what you do is that find the derivative of this and see whether you get sine squared x. That's what this is saying. Okay. The last bit has to do with rate of change. Okay. This says total change theorem and application. So we want to apply the so-called total change theorem, what we just looked at there, the evaluation theorem, okay? The integral of a rate of change is a total change. In other words, if I integrate from a to b, let me move this, a to b of f prime dx, remember f, capital F is the antiderivative of something, right, of a small f. In this case, if I integrate this is a derivative. If I integrate it, I'll get back the function big F, but in the form f of b minus f of a. All right, we know this. So this says that if an object moves along a straight line, right, with position function s of t, then its velocity vt is given by the derivative of the position. If we differentiate the position function, you get a velocity. All right. So the integral from time, let's say t1 to t2 of the velocity will be equal to the integral from t1 to t2 of course, the velocity is the derivative of the position function. So that is this. But because we have a derivative in here, if you integrate it, the derivative goes away and you are left with a function, the s. And so you can just plug in your limit and you have s at t2 minus s at t1. Okay? And this is the change of position or displacement during the time interval from t1 to t2. So in other words, if you are given the position function, right, it's straightforward, okay, to compute its velocity, which is given by this, just find the derivative of the position. If you integrate the velocity, right, remember in the distance problem, right, if you integrate the velocity, right, sum up the various things, you're going to get the change of position or displacement. Okay, so that is this. The total distance traveled is given by the integral, right, from t1 to t2 of the absolute value of the velocity. Okay, so this is back to the distance thing, where this is the speed. Okay, the absolute value of this is giving you the speed. So let's look at this here. So if this is velocity and this is time, this is changing. The velocity is changing with time. It's changing with time. You can compute each of these, which will give you the distance along, right? So the A1 will give me the distance traveled from, if you want T1 here to this interval, to this point here, right? Then from this point to this point will give me A2. Because A2 is negative, that's why I need to take the absolute value. Then I get a positive quantity. That's the distance traveled. And then this one will give me the other part of it. Okay, now the acceleration of the object A is the derivative of the velocity. Okay, so if I integrate the acceleration, of course, I can plug in V prime here. And if I integrate V prime, I get V at T2 and T1, okay? And is the change in velocity from T1 to T2. So if you integrate the acceleration, you are going to get a change in velocity of the object from time T1 to time T2, okay? So integrate the acceleration, you get change in velocity. Integrate velocity, you get a change in position. That's basically it. That's the lesson here. Okay, so that brings us to the end of this lecture. Okay, if there are any questions, of course, feel free to let me know. Then we can address that, or you can bring them up when we're having maybe tutorials and other things. Okay, so all the best with this lesson on this thing on integration.